Hello my friends, welcome to the beginner's tutorial for learning CNN. We are going to talk about how to use CNN that has been previously trained for classification and later on use it for regression activities. This project is very easy to follow and suitable for data scientists who are starting to learn CNN. This is gonna be exciting. Let's dive straight into it. Let's get started. In this project, we are going to detect street nameplates. Street nameplates come in a range of unique shapes but are rectangular in nature. We are going to use a convolutional neural network or CNN to perform object localization on the street nameplates. For training purposes, we must draw a rectangle around a street nameplate. Something like this. These rectangles are usually referred to as bounding boxes. We must then save the bounding box information into an XML annotation format. Here is an example of an XML file. This XML format can capture image file name, image file path, image size, and definitely bounding box coordinates. A CNN typically consists of three layers: convolutional layer, the flattened layer, and the fully connected layer. This CNN performs the multi-class classification to determine whether the image contains one of the following animals: a cat, a dog, or a bear. However, in this project, the CNN will be used to predict object location. For that purpose, a new fully connected layer will be created, and the CNN output would be a predicted bounding box. The street plate name image enclosed by the bounding box then fed into an object character recognition tool or OCR. The OCR will extract the characters out of the nameplate image. To load images into our Python program, we can use an OpenCV function called imread or a keras function called loadImages. The difference is the loaded image would be in different formats. On the left side, the loaded image is in a BGR format by OpenCV. On the right side, the loaded image will be on the RGB format for keras. Keras is to support machine learning or neural network tasks. OpenCV is mainly to support computer vision tasks. Since we are going to do deep learning tasks, to avoid installing many packages, we'll use the keras load image function. Normalizing training images. Normalization is required because training images have different heights and widths. So here is some examples of different images. They have different height and width. On the other hand, our pre-trained CNN expects all of them to be the same size. For example, this size 224 by 224. Since the sizes of the training images are different, most probably the sizes of bounding boxes are also different. So we use the following equations to get normalized size of the bounding boxes. For that purpose, we need to get the height and the width of an image and as well as the bounding box coordinates such as xmin, ymin, xmax, and ymax. Floating point. Weight of a CNN should be represented in a floating point format. The question is, which format? 4, 16, or 32? In the 32-bit floating point, we reserve 8 bits for the exponent and 23 bits for the mantissa. It is found out that in most deep learning use cases, high precision and wide magnitude is not required. Most weight and gradients tend to fall within 16-bit range, or FP16. However, using FP16 poses some risks. We are not going to discuss about this here. Therefore, we use the 32-bit floating point because it is the most supported by hardware and software. Train test split procedure. This procedure will arrange a dataset into features and target. Then it splits the dataset into a training set and a testing set. Then use the X train and Y train for training the model, and X test and Y test for testing the model. Pre-trained CNNs. To speed up the process of creating a new CNN model, we use a pre-trained CNN. The following are a few examples of pre-trained CNNs from TensorFlow. What we can see here, Inception ResNet v2 has the highest accuracy. Then let's use this model. Although the model size is quite big at around 215 megabytes. Right, this is a block diagram of Inception ResNet v2. So it is a CNN that is trained on more than 1 million images. The network itself is 164 layers deep and can classify images into 1,000 object categories. As a result, the network has learned rich feature representation for a wide range of images. The network has an image input size of 299 by 299. However, in our project, the image input size is 224 by 224 due to hardware resource constraints, especially the GPU memory. How CNN performs a classification. So here is a CNN architecture for a classification task. First, the convolutional layer performs feature extractions, and then followed by the flattened layers, flattens out the feature maps into a feature vector, and finally the fully connected layer takes this feature vector for the learning process. At each output node of the FC layer, a softmax filter is attached for performing declassification. How CNN performs a localization. For localization, we need two types of images. An original image and an image with its corresponding bounding box. We still use the same convolutional layer used in the classification case, and also use the same flattened layer but a different fully connected layer. Instead of the softmax filter, we attach a sigmoid activation function to each output node for regression task. Regression task requires loss functions for adjusting the neural network weight. CNN code. So here is a snapshot of CNN codes. So we use Inception ResNet v2 and alright, so this one actually the Inception ResNet v2, and then we flatten the feature maps using this command flatten, and finally we create a new network here that use sigmoid activation function at the output nodes. So here we have 4 output nodes: xmin, ymin, xmax, and ymax. How CNN performs the localization training. So here we have expected bounding box coordinates. With this info, we can start the learning process. First, initially all FC layer weights are initialized to 0.1. Then the feature factor is applied to FC layer. The FC layer is assumed to generate new BB coordinates. Okay, so this is assumed to be a new BB coordinate. Based on the new coordinates, the FC layer calculates the loss and back propagates it to adjust the weights. So the FC layer actually calculates the loss and propagates to adjust the weights, and then apply the feature factor to the network with the updated weight and assume it produced these new bounding box coordinates. Repeat step 4, 5, 6 for the next rounds. When it reaches 0, then we have reached the first epoch. Epoch, batch, and iteration. An epoch is a combination of a forward and backward propagation of the whole training set. Within an epoch, we can specify how many records will be processed simultaneously. Assume we have 520 records. If these 520 images are processed simultaneously, it only requires one iteration in one epoch. However, your machine may not be able to handle this. So, instead, those 520 records will be divided into several batches. As a result, one epoch may contain several batches in one iteration, resulting in many iterations, and it will take longer time. But how many epochs are required? Use early stopping to utilize the flexible number of epoch method. In general, the more epoch, the better. Compile parameters. There are 3 parameters we need to specify: the loss, the optimizer, and the matrix. An example of a Python code here. So as we can see here, the loss is specified as MSE, optimizer is Adam, and matrix is MSE again. Optimizer. There are several optimizers: gradient descent, stochastic gradient descent, mini batch SGD, SGD with momentum, ADA grade, RMS prop, and Adam optimizer. Here is the comparison of optimizers. As we can see here, Adam optimizer is currently the best optimizer on the market. So Adam configuration parameters. includes alpha or learning rate or step size. Larger values mean faster learning rate. Smaller values means much slower learning rate. The second parameter is beta 1. And the third one is beta 2. And the last one is epsilon, a very small number to prevent division by 0. But most of the time we only specify the learning rate or the alpha. L2 loss function. Loss quantifies how well a model performs during a training phase. L2 loss is the square difference between a prediction and the actual value calculated for each sample. L2 loss penalizes large errors happening in the bounding box regression. MSE regression loss function. If we sum all L2 values in the previous example and take their average, then we'll get a cost function called MSE, or mean squared errors. Hence, an MSE equation becomes like this, where n is the number of observations. Monitoring the training and validating process. What we can observe from the following trend and validation loss plots is overfitting. Overfitting happens when train loss keeps decreasing while file loss is stable or keeps increasing. There are several ways to address the overfitting: adding more training data, data image augmentation, dropout regularization, L2 regularization, and finally reducing network width and depth.